Yeah, so thank you for the chance to come here. I've never been here before, and to talk about this stuff. Let me mention that the main results I'll be discussing are joint with Brian Williams. All this sort of the framework is developed in work with Kevin Costello, sort of broader framework. So this talk will be about, maybe I should just write over here the summary, sort of the goal of the talk. And the talk will be aimed at explaining what the terms mean. So study symmetries of holomorphic field theories. In a uniform way, meaning sort of working over different dimensions, not just in, say, complex dimension 1, allowing systematic generalizations of results from chiral CFT on Riemann surfaces. So the main goal of the talk is more or less to see how there's a generalization of the affine Lie algebras, which show up in chiral CFTs on Riemann surfaces, to higher dimensions. So I'm going to do sort of foundational background stuff right now, give some context and some techniques, and then Brian will explain some work he's currently pursuing that puts this stuff to has some very non-trivial applications. So I need to tell you what I mean by holomorphic field theories. We've had two talks today that sort of focused on topological field theories, so I want to talk about holomorphic field theories. I'm going to do that by example. I'm not going to give an axiomatic definition. So I'm going to study relatively simple examples, but hopefully it'll be clear how to generalize. Suppose I'll use X for a complex d-dimensional manifold. So one example to bear in mind is known as the beta-gamma system. There's two fields, gamma and beta. So gamma is going to be a smooth complex valued function on X. Beta is a Dolbeau form. So this was, if you'd like, a 0,0 form on X. And then the action is this. So if you apply del bar to this, you get a 0,1 form, and a 0,1 form pairs with a d minus 1 form to get a top form. So you can integrate. So the equations of motion here, the Euler-Lagrange equations, are that del bar of gamma equals 0 and del bar of beta equals 0. So at least to a mathematician, that's a very beautiful theory. You're picking out holomorphic functions as your sort of on-shell fields. There's an obvious fermionic variant. So that's all bosonic. There's a fermionic variant, which is the BC system. And all I do is switch the parities here. So C But you can do other examples. You can do the curved beta-gamma system or holomorphic field theories. So you could do curved beta-gamma system. So here, gamma would be a smooth map from X to some other complex manifold Y. And beta would be a d minus 1 section of the pulled back cotangent bundle. you could do holomorphic gauge theories like holomorphic Chern-Simons. So these are field theories to bear in mind, and then we'd like to understand how symmetries act on them. So let me introduce what I mean by symmetries. And I'm going to focus on the beta gamma system today because it's a very easy system, and hopefully you can track what's going on there pretty quickly. So the solutions to the equations of motion are holomorphic, say in particular holomorphic functions. So what I'm going to do now is modify the fields by having them take values in a representation of a Lie algebra. And then if the Lie algebra acts, of course, it'll preserve the space of solutions. So in particular, let's imagine we have a holomorphic principal bundle. G is some complex Lie group. Think like SLN. And V is some finite dimensional representation of G. Then we get some associated bundle. And now I'm going to have my fields be sections of this bundle. So gamma now will be a section of coefficients in V. And beta will be a d minus 1 form in the dual bundle. And then I have the same action functional, but now I use the evaluation pairing between V and V dual to get a top form. And I get the same equations of motion. So now solutions are, again, holomorphic sections of V. So solutions the holomorphic sections so on and so forth. But now I have an extra symmetry to take advantage of. There's the automorphisms of the principal bundle, which will act on these solutions as well. So so let me say that, OK, there's going to be an action of the Lie algebra. So this is a kind of charged beta gamma system. So I like to point out that if you have a holomorphic section alpha of the adjoint bundle, preserves solutions to the equations of motion. If del bar of gamma equals 0 and del bar of alpha equals 0, then del bar of alpha times gamma equals 0. And this is just a point-wise action. At each point in x, you're getting an element of the Lie algebra, and you're acting on the fiber V. So this is an example. This is a holomorphic. That's what I mean by a symmetry, a holomorphic symmetry of the charged beta gamma system. So I'm trying to give a gloss of what the talk is going to deal with. So here's holomorphic field theories, here's symmetries, and now with this on the board I can give you the flavor of the kind of result we're aiming at, and I'll spend the rest of the talk trying to make that precise. So we will study this system, this situation, using the Batalin-Vilkovisky formalism as articulated by Kevin Costello. So we're going to use some of his renormalization techniques and the language of factorization algebras and things. And so the flavor of our results looks like this. Well, we have sections of the adjoint bundle as a sheaf of Lie algebras, holomorphic sections, and it's acting on space of solutions to equations of motion. And this ends up being encoded in the following kind of information. So there is these are factorization algebras, or chiral algebras. And this one is supposed to be the observables of the classical field theory. So it's the commutative algebra of functions on the fields with some extra structure. Now there's also another chiral algebra. This is CUR for currents, these classical currents, which are sort of determined by the symmetries. The idea is that there's a map that takes every symmetry to an observable. So this map sends a symmetry, e.g. alpha here, to an observable depending on alpha. So this is sort of the Noether theorem in action. Symmetries determine observables. Now, in the Batalin-Vilkovisky formalism, when you quantize, you end up producing a deformation of the classical observables in a way that depends on h bar. So there's a sort of dequantization map. This is much like deformation quantization, where you have an associative algebra in powers of h bar such that modulo h bar you get back a commutative algebra. This is also a chiral algebra, a factorization algebra. And the kind of question we're going to ask is whether we can lift these symmetries, or these observables in the classical, these observables that come from classical symmetries to quantum observables. And so the answer is typically you can't lift. So typically you cannot lift J classical to a map into the quantum observables. And the obstruction is a holomorphic version of the ABJ anomaly. So one goal is to actually write this specific anomaly down explicitly. Okay, but once you find this anomaly, then you can introduce a deformation of the classical currents to the quantum currents. Let me give this anomaly a name. Let's call it theta of v, because it's going to depend on v and the way the Lie algebra acts on it. This is also dequantization. And there'll be a map of chiral algebras from some sort of factorization algebra of quantum currents to the quantum observables. Things like Ward identities can be read off from this map. Okay.
Do you literally mean that there's a map on the left-hand side of a vertical map?
Yes, there's a vertical map. This is also mod h bar.
Twist the domain of that by the gerb classifying data.
how about you ask this a question again in like 40 minutes and see if my answer, yeah. We're going to modify the Lie algebra of symmetries using that cocycle, so we get some sort of L infinity extension, and then there's some interesting factorization algebra you get out of that. It's like the enveloping factorization algebra. Okay. So one upshot of one thing you can read off of this map, in particular by compactifying along the spheres. So there's a natural map from the punctured d-dimensional space down to the positive reals, which is taking the radial projection. So this goes to the length of that vector. And the compactification of this map along R recovers sort of results of Founta, Hennion, and Kapranov on higher Katz-Moody algebras. So, so these three authors introduced some L infinity algebras or higher Lie algebras that include in the dimension 1 case the usual affine Lie algebras, but generalized into higher dimensions, and showed they had a nice systematic relationship with sort of higher versions of the affine Grassmannian and of the moduli of G bundles on higher dimensional spaces. And what we'll see is that we're giving sort of the complementary physics story about how the sort of Lie algebras they write down, these higher Katz-Moody's, actually act as symmetries on observables of holomorphic field theories. So that's sort of how we're going to see this systematic generalization of results from chiral CFT. Okay. Any questions so far? So this is the target of the talk, is to understand these statements. So now, I said I was going to use the BV formalism, so I just want to revisit the description of the theories and the symmetries in the BV style. So let's do the classical BV theories. And in practice, this is just going to sort of mean doing everything in a differential graded way. So gamma is no longer just going to be a smooth function. It's going to be an element of the Dolbeau complex values in V. And beta is going to be in the Dolbeau complex of holomorphic D-forms with coefficients in the dual bundle, but with a shift. So I should say here D is going to be the dimension of X. And typically, just for simplicity, let's always think of as just the d-dimensional space. Well, so this means we have a graded space of fields. In degree 0, we have omega 0, 0, coefficients in V. And then the beta field is d minus 1 because of the shift I gave. So the stuff in cohomological degree 0 is exactly the sort of naive theory I wrote down before. But now I've introduced these other things. So this is all zeros in the gamma part. But down here I have omega d 0. What I want to point out, if you're familiar with BV, is that, of course, like these fields have their antifields being here. The antifields of this field is here. These are partnered up as antifields. So there's this pairing, if you'd like, on the fields evaluation pairing on V. You just wedge use the evaluation pairing between V and V dual to get a form is a pairing of degree -1. We think about it as kind of providing the space of fields, this DG space of fields with a shifted symplectic structure. So let F denote this sheaf of fields. So far, I've been talking about everything being on the whole space X, but of course, I could keep track of, use different opens in X and think about sections over a given open subset. So F will be a functor from opens on X to, in this case, we could say chain complexes. And it's going to send the open set U to the Dolbeau forms on U. That's where gamma lives, plus the D forms on U shifted by D minus 1. OK? And this is just sort of the obvious. Sorry, there's an op here. If I have fields on a bigger open set, it restricts to fields on a smaller open set. Now if I take functions on fields, maybe I should say what I'm trying to do. I'm trying to tell you what this thing is, very briefly. The classical observables are functions on the fields. I'm going to be thinking about sort of polynomial or power series style functions, because these are actually sort of DG vector spaces. And I'm totally going to suppress the function analytic issues you have to bear in mind. So they define a functor the other way to commutative algebras in chain complexes, which I'll loosely speaking say is functions on f of u. So something like the symmetric algebra on the linear dual of f of u. Polynomial functions on the fields. OK. So not using the board space very efficiently. One of the things I want to point out is that it has a certain, there's a picture to bear in mind to relate to the thinking about things like OPEs. If you have some big open set and two smaller disjoint open sets inside of it, there's this since a field on the big open set V restricts to a field on U1 and one on U2, functions go the other way. You can pull back functions from these smaller open sets, from fields on these smaller open sets to fields on the big one. That's this map from this Hobbes classical. But we know that the fields on two disjoint open sets is equivalent to the fields on one open set, direct sum of the fields on the other open set, which means that this thing is actually the tensor product so if I have an observable on U1 and an observable on U2, there's some way of putting them together. You can take the measurement you make in U1 and the measurement in U2, and you multiply their outputs. And that's this composite map, and that defines an observable from the big open set. When we quantize, this structure gets deformed, and you can read off of it things like the OPE in vertex algebras or in chiral algebras. OK. what's something else I need to comment about? So these fields were actually a DG algebra. We had this differential, I should have drawn it, sort of del bar here, which are imposing the equations of motion. So Hobbes classical has a differential arising from del bar as well, because it's functions on a cochain complex, symmetric algebra. But it also has a one-shifted Poisson bracket, often called the BV bracket or anti-bracket, which just comes from this pairing here. So there's this kind of, this vector space is like, the fields are like a shifted symplectic thing, so functions on it should be a shifted Poisson thing. Arising from this pairing on F. And actually, one of the things you can check is that the differential on the classical fields is the bracket with the classical action functional. So we'll use that later when we quantize. Okay. So now I want to describe the sheaf of symmetries. Which is going to be the Dolbeau version of the holomorphic things we said before. So let's define script G here to be the sheaf of Dolbeau forms with coefficients in the adjoint bundle of P, sort of. If we're on flat space, then G just looks like the Dolbeau forms, tensor R Lie algebra G. So it's a nice DG Lie algebra. And G acts on the fields in a pointwise way. Because the Lie algebra acts on V, yeah, I guess way up there, any section of this, I mean, this is like smooth sections of something, Dolbeau forms is a commutative DG Lie algebra. And that's with values in some representation V. Of course, G acts on V, so you can extend it over this commutative DG algebra to get an action. But if you have an action on a space, then you also have an action on functions on the space, which, if you'd like, can be, this is a Lie algebra map. From G into derivations. This is, of course, I've been calling the classical observables, into the classical observables. So these are vector fields, if you want. On F. OK, so far so good. So we have this Lie algebra map. But I've just told you we're thinking about things from the point of view of Poisson geometry. Like we have this Poisson structure we can bear in mind. So one question we could ask is, sort of mimicking what you do in Poisson geometry, there's a map from functions on F to vector fields on F, taking the Hamiltonian vector field. And you can ask if we can lift this map. OK, now I get to use this thing here. So we have this map to derivations of functions on fields. We also have a map from functions on fields with a funny shift because it's a one-shifted Poisson bracket. So this sends a function f to its Hamiltonian vector field. This is the Hamiltonian vector field. You can ask if you can lift this map, which would exactly be realizing a symmetry as an observable. And the answer is you can. And the map is very simple. So the observable for some element here on beta gamma is going to be the integral of beta. You just let alpha act on the symmetry alpha act on a field, and then you pair it with beta like you did before. And that's an observable. So a symmetry determines an observable. Note that it has the same form as the kind of flavor as the action functional. It's local on x. It's an integral over x. I want to raise a simple but important point here, which is that this formula is very simple, but you could ask, when is it actually integrable? We want it to be an observable on all fields, so there's no reason to suppose beta or gamma are compactly supported. So if alpha were non-compactly supported, this whole thing might not be something you can integrate. So we're going to have to restrict alpha to be compactly supported to guarantee that you always get something you can really measure, so an actual observable. So simple but important point, which I haven't seen sort of emphasized in the physics literature, though maybe it is somewhere I haven't seen, is that you need alpha compactly supported. So really, I'm not going to work with this sheaf, but a certain co-sheaf, or pre-co-sheaf, I should say, to the algebras. It's going to send U to the compactly supported Dolbeault forms on U in this adjoint bundle. So this means compactly supported. And this is good, because I want G to map to the classical observables, right? And the classical observables is a functor this way. So it's a pre-co-sheaf rather than a sheaf. You see there's an op here. So this is a good thing. So actually, instead of having G go to functions here, we have a map of pre-co-sheaves of Lie algebras, which I'll call J classical. And this is a map of DG Lie algebras, of pre-co-sheaves with D Lie algebras. Okay. So we're doing this sort of stuff we did before, just taking into account the variance in terms of space-time support. So this map, J classical, there's two different ways to rephrase it that I think are suggestive and that will be useful when we quantize. So two variants. The first one is to rephrase in a way that looks like a moment map. So this is sort of a moment map style. So let's just recall how the usual moment map picture works with the unshifted Poisson stuff, and then we'll just do the shifted version. So if M is a symplectic manifold, then in symplectic geometry, we're typically interested in G acting by Hamiltonian vector fields. So we have some map of of Lie algebras. Of course, you can post-compose with derivations on O of M, and this is taking the Hamiltonian vector field. But this map of Lie algebras, this thing on the right is not just a Lie algebra, it's a Poisson algebra. And you could ask, well, can I extend this map to a map of Poisson algebras? And there's a very simple way to do that. You can just take the symmetric algebra on G. So it's commutative structure, just the usual multiplication of polynomials. But then you extend the Lie bracket to a Poisson bracket in the canonical way. Now there's a map of Poisson algebras into functions on M. So this is if you'd like, the enveloping Poisson algebra It's the left adjoint to the forgetful map from Poisson algebras to Lie algebras. But you could think about this, if you'd like, as functions on G dual. So this induced map of Poisson algebras is pullback along the moment map. So this is pullback of functions along the moment map from M to G dual. Okay? So this is just, you can go back and forth between this data to give a map out of this enveloping Poisson algebra is the same thing as just to give a map of Lie algebras. So this kind of data, or this kind of data, they're equivalent, but this might have a more geometric resonance with you. Now I'm just going to do the same thing, but in the one-shifted context. So I'm going to tell you what this thing is now, and this map will be the one-shifted version of the map of Poisson algebras there. So define the functor of currents, which will just be taking the symmetric algebra on this pre-Cauchy sheaf. So it's going to go from opens in X to one-shifted Poisson algebras, category of one-shifted Poisson algebras, dg, of course. And J classical determines a map, which I'll also call J classical abusively, from the currents. So this shift here cancels out this shift here. So this is a map of pre-Cauchy sheaves of shifted Poisson algebras. And all it's doing is turning every symmetry into an observable, and polynomials and symmetries if you want. Okay, and you can think about this as a co-moment map. So this is a one-shifted co-moment map. Okay. I find that helpful for porting intuition from symplectic and Poisson geometry into this one-shifted setting. Okay, so that was one way of rephrasing or re-encoding this map that's sort of attractive, and it's told us one part of our problem. The second way is going to be more in the style of field theory. Which is that map there, J classical and alpha, that looks like a local functional. It looks like part of an action functional. So why don't we view alpha itself as some sort of background field? So, okay. View alpha G as a background field. So we have a space of equivariant fields, which will be the direct sum of F plus G. And the equivariant action will depend on alpha, beta, and gamma, and it'll be the original action which, if you'd like, you could write You're right. Okay.
Sorry, Owen, on the last line there, should there also be a shift on the left?
Where? Here?
On the right here, obscure.
No, this shift, sorry, they're supposed to be right there. Yeah, sorry, I did it here, but I didn't put it there. Yeah, they cancel out. Okay. So now, one way to understand what I'm doing here is as a baby version of causal duality. So this is a baby. Okay, so then the equivariant observables will be functions on this thing, and I claim that it looks like the Lie algebra cochains of G with coefficients in the original classical observables. Okay. And the differential here, the equivariant version of the differential is just bracketing with this, sorry, equivariant action. Let me just explain, that may just seem really arbitrary unless you're familiar with this kind of construction. So let me elaborate that it's basically a baby version of causal duality. This is a baby version. To give a map from a Lie algebra G into, say, A. So let's say this is a Poisson algebra, and this is some Lie algebra map, rho. Well, this means that rho of a commutator should be the commutator of rho applied to the inputs. Okay. But to give such a map is equivalent to giving a more Cartan element in the Lie algebra cochains of G tensor A. And why is that? Well, if you use the Chevalier-Eilenberg differential applied to some element rho and evaluate it on x wedge y, that is rho of the bracket. And if you, sorry, this should be a Poisson bracket. And this thing corresponds to 1/2 of rho wedge rho evaluated on x wedge y. So up to a sign, the Moore Cartan equation is equivalent to this condition. Okay? So encoding, so under this correspondence, giving this map J is the same thing as picking out a Moore Cartan element in here, which is exactly picking out this sort of this interaction term, if you want, or yeah. Okay. But I want to say there's this fancy way of saying it, baby version of causal duality, but basically as a physicist you would just be thinking about having a background field determined by that thing. Okay. So now we want to quantize this.
Excuse me, before you quantize, what have you achieved by generalizing this, the usual non-formalism with being the completely covariant? There's only a finite number of concept currents or concept charges. Then now you have this full d-dimensional integral that allows you to play with the variational structure, but the content is the same.
Yeah, the content's the same. I totally agree. Maybe one thing is that this is all like, I'm not saying that this part is particularly interesting. There's nothing sort of, I just think it's a nice language for talking about symmetries. I think the quantization is sort of the interesting bit. Brian, like, do you have anything you would add? No?
Maybe later.
Yeah, okay. Yeah, it's basically just the Noether formalism articulated in this DG setting. Okay, but now let's get to the interesting part. So the loose idea of BV quantization is we want to deform the differential on the classical observables to a differential, I'll call Q on, we can do power series in h-bar polynomials depending on the situation, such that two things hold. One, this is just the classical differential, but plus things that are order of h-bar. And the crucial condition is that on the product of observables, the quantum differential fails to be a derivation for the algebra in a way that depends precisely on the bracket. Okay, so the Poisson bracket is telling us how to deform the differential, much like how in deformation quantization the Poisson bracket is telling us how to deform the product. You just shift the setting of the problem here. And let me remark, thus the quantum observables, if you can find them, which is exactly the classical observables with dependence on h-bar in this differential here, still has, well, okay, so this is still a functor, but now it's a functor from opens to dg modules over h-bar. But this differential is still a derivation for the bracket. So it's not a derivation for multiplication, but it is for the Lie bracket. So the kind of question you can ask is, can we lift this map here this mod h-bar map is a map of DG Lie algebras, and you can ask whether you can lift. Okay, it's about quantizing the symmetries. So the most tractable way to approach this problem is actually by this background field method, because what it does is it expresses the whole problem as what looks like a BV field theory, and then we can try to use perturbative methods to actually quantize. So it's probably, in some ways, the least attractive one for thinking, but it's the most convenient one for actually doing constructions. So now I'm just going to sketch what happens very briefly. So if you look at that, so let me just remind you of this equivariant action. And if you're used to doing perturbative stuff, you can tell that this thing tells you what your propagator is. Just if you start doing the Feynman diagrams, this is telling you what the propagator is. And then you have this trivalent vertex. And you can ask, if I try to quantize this just in the usual way, what kind of graphs show up? Only very simple graphs show up. There's things that look like this. The tree level stuff. Gives you this kind of thing, which is sort of encoding sort of an L infinity description of the same DG Lie algebra. And you also get wheels. But these wheels only have alpha as outer legs. So the diagrammatic quantization, so the Feynman diagrams, produce sort of a quantized, let's say this is the naive thing. We'll have to check the master equation in a second, which looks like the original equivariant guy. This is the tree level stuff, which depends on alpha, beta, and gamma, plus an interaction term that only depends on alpha. So this is the wheels, the one loop terms. And there's no higher terms. OK? So the question becomes, trying to give a lift of this map is the same question as asking, sorry, just as a remark, the statement that this thing is a differential is called the classical master equation. And so being a more Cartan element is a solution of the classical master equation. And this is going to be the quantum master equation. Which is the same thing, but replacing this Poisson algebra by the quantum observable. So solving whether it's a more Cartan equation. OK. And the answer is no. So let me explain what the answer does look like. I'm not going to elaborate on this because I didn't give myself time, but one of the nice things Brian's done is to sort of do once and for all computations that work in every complex dimension that lets you know that the one loop terms that show up in theories of this flavor don't require counterterms. So we're going to use his analytic results to say that we don't need to stick in nothing singular. We don't have to stick in counterterms here. And so the problem just boils down to checking this thing about the quantum master equation. And the quantum master equation, you're asking, let me not, given the amount of time I've given myself, the failure to satisfy the quantum master equation is a particular co-cycle. So let me just state our main theorem. The co-cycle obstructing solution to the quantum master equation, meaning if I stick it in, if I do dq SQ equivariant, Chevalley-Eilenberg SQ equivariant plus 1/2 I'd like to know whether this thing is 0 or not. Being 0 would mean it's a more Cartan element. But if it's not 0, that's my cocycle. So this cocycle on x equals c to the d is given by the following. It takes in d plus 1 inputs of alpha. So only the wheels that have d plus 1 legs survive as anomalies. The trace over V so here rho denotes the map from the Lie algebra to endomorphisms of our original vector space V. So I'm taking some form with coefficients in G, and I'm using it to make a form with coefficients and endomorphisms, and then I wedge them together. I do the dels on D of the inputs and no del on the first one. So the del adds a 1, makes it sort of a 1-0 form. So I get D10 forms, and then if you pick the alphas appropriately, you can get a top form. So this is the cocycle. This, if you're familiar with the ABJ anomaly, this looks like a version of that. So this is ABJ-like. There's no d-bar, just del. Yeah.
Alpha d-bar forms.
I mean, the alphas are elements of 0 star forms.
And there's no del on the 0 term?
No.
Otherwise, you couldn't, yeah, you can only have at most d. Yeah. So this cocycle determines an extension of GC as a pre-Cauchy of L infinity algebras. So let's call that G theta of V. The underlying space looks like this. Here, h bar has degree +1. Has the same L2 is the bracket on G, but L d plus 1 takes as inputs is exactly this cocycle, so it's theta. So this cocycle determines an L infinity extension. And now this new L infinity algebra is quantum symmetries. Does lift to a map. I'm going to modify that in just a second. So quantum observables. So there's this dequantization map. There's J classical. The obs classical shifted by -1. It's quantum shifted by -1. And there's a commuting diagram. These vertical maps are modulo h bar. So this classical symmetry doesn't lift, but you can modify the Lie algebra to an L infinity algebra, and that does act as symmetries. So every element of this L infinity algebra gives you an observable in the quantum system. Down here we had a one-shifted Poisson algebra. Over here we have a BV algebra. And just as you can, there's an enveloping, just like the symmetric algebra was the enveloping functor, the enveloping Poisson algebra, the Lie algebra chains actually there's a factorization algebra obtained by taking Lie algebra chains of this thing here. And then get a sort of quantized version using this left adjoint between the factorization algebras. Okay. So that was the sort of main goal. I was going to explain how it relates to the work of Fanta, Henyan, Kapranov, but I've run out of time. So at least I accomplished the main goal. Okay, thank you for listening.
Are there any questions?
But this is a bit confusing. In your algebra, you get extra one dimension. That's this h bar. So cochains, when you consider cochains, you get something like formal power series in h bar. Yeah.
Yeah.
I see.
Other questions?
If X isn't flat space but is something curved, can you still calculate the examples, so you can still calculate the abstraction?
Brian's nodding, yes. Brian's the great computer out of the two of us. If you want a wrong answer, you can ask me to do a computation. But.
Any other questions?
Sorry, I didn't listen to your question, but can you consider X as any manifold?
Yeah, it's just that you can sort of take any complex manifold, and you can try to do the computation. It's just that there's no reason that you should have such a simple form for the abstraction. Yeah. It just might be hard to compute in practice.
Okay, if there are no other questions, let's thank Owen again.